Okay. So, so I'll give a very brief introduction to one of our to some work that we have done, and we are augmenting on it. And I picked this because I think this kind of fits in well with the broad theme of generative models that we're talking about. And until now, we have been really talking about generative models for the static part of the graph. That you have the static structure, which is really the skeleton. And what kind of things and how can you come up with models to try to understand these different properties, right? I mean, what this work represents is trying to come up with the generative model to capture the information flow, the information dynamics in a network, right? So while this, when I'll talk about the model, this work was primarily done keeping Twitter in mind. Right? However, as I'll sort of try to point out at the appropriate places, there's nothing specific about Twitter. It's really about a process that's running on a network, that process having certain characteristics, right? For instance, that process having that process being described by a feature vector, which is not always completely observable, which is noisy, and this process is running on the network, and different users are influencing their neighbors in participating in the process, basically. And think of this process as just, in this setting, this process has been just writing a tweet on a particular topic. Okay. However, as you will yourself sort of hopefully, think about other examples in which to apply this to, and I love to hear them. Right. I've been talking to some biologists, and I think we can figure out applications of this modeling of this particular way of modeling in terms of biological processes that sort of are propagating over networks. Okay. So this work is mainly the work of my PhD student Jayesh. So any sort of good things have been done by him. All the errors I should own up to, if you find any bugs or typos in the slides. And this is joint work with Srikanto, who's at this should be Triple IT Delhi at this point. And Indrajit, who's at TCS Research, TCS Innovation Labs. Okay, so the title is a mouthful, but we'll slowly get to it. Right, and so while there are a bunch of sort of probabilistic things, again, what I'll sort of try to sell is really the story behind it, not so much underlying mathematics, but what is the story, and then where exactly do we need to bring in what components of math tools? That's what we'll try to sell. Okay. So here is the broader story, right? That suppose to consider a network, right? And as I said, think of this network as either the Facebook network or the Twitter network, in which users are connected with each other. There is some underlying hidden weight of connections, right? And this maybe captures how one user is influencing another. Right? For instance, if this user sort of writes about certain things, right? There is maybe, it maybe sort of increases the chance of this user writing about similar things or about related things by a certain factor. And this value that I've written captures that factor, right? Abstractly think of it as how much influence user 1 has on user 2. These values are obviously not observed. And we will try to deduce these values from the model, right? Each of these users is writing about certain topics, right? If you make a tweet today, it will be about certain topic, right? What do I mean by a topic? A topic mathematically. So okay. So first, intuitively, a topic is really, so think of an abstract clustering of the set of tweets, right? There are some tweets about politics, some tweets about sports, some tweets about Indian politics, some tweets about US politics. These are subtopics of the politics topic. Some about baseball, some about football, and these are the topics. These again are not observed to us, right? But what we do have is, for the tweet or for whatever action that is happening, we have some observable features. In the tweet case, the observable feature is really the content of the tweet. This is what is observed to us. If it's some other process, if it's some biological process, we have some things that we have measured for the process. Right? We might not know exactly what category to put that process in, but have observed some properties of the process, right? and there are different things that are happening, right? So I mean, there are things that are happening in terms of users. For instance, if you really follow if you really like certain people, right, or if you're influenced by certain people, if that person writes about some certain set of topics, he will tend to write about related topics, right? This is the user influence. Right? There are also, I mean, the inherent temporal dynamics of every user, right? And maybe at this point, you are just interested in sort of this kind of topics, and you keep on writing about those, right? I mean, you also have some natural preference topics. I mean, I don't want to write about IPL. I don't see IPL. So even if IPL is happening today, I won't maybe put out a single tweet about them. Right? So there's some user preference. I mean, there's some user topic preference, right? And then there's this network strength that we said. So most of these are not observed by us, right? I mean, I'll tell you what the data that we actually see. We don't get to see the preferred topics of any user directly because I mean, I don't even know what topics are because, I mean, topics, so think of topics as really clusters. I don't know what clusters are until I've actually clustered the data. And really, I mean, it's not possible to say a priori what the preferred topics of every user are. Right? So this is happening on the user side. If you just regard the user, I mean, but there is something more actually, right? If you, for instance, look at the topics themselves, right? So forget the users. Just look at topics themselves. For instance. I mean, okay, so this is about some set of shootings that happened in US. I mean, and this is a word cloud of a bunch of tweets. Okay, the Gabriela Giffords, I mean, she's a US senator. She was a US senator. She got shot, and this is a word cloud of the set of tweets that contain this topic. This is about some movie-related tweets. Word cloud of that. This is about some cyclone-related tweets. This is about the NASA space launch, and it's possible that some of these topics are more tightly related to each other than some other ones, right? It's possible that that today any tweet about Gautam Gambhir maybe is more tightly related to Indian elections than a tweet about Sachin Tendulkar, right? So there is also this topic influence, right? What I mean by that is that if I today go on Twitter and tweet about how good that last speech of Rahul Gandhi was, somebody who's following me will likely tweet about how better the speech of Narendra Modi was, right? So although this may or may not be the same topic, there's at least some direct correlation between them. One of them influences the other. Having somebody write about one of these topics influences the other person who's reading it, potentially influences the other person to write about the other topic, right? Yeah. And this is also something that is not known to us, right? We don't know these clusters. We also don't know, of course, how each of these clusters influence one another. Okay? So this is the very high-level setup that we have. Yeah. These links are directed. These links are directed. So think of the follow links in Twitter. They are directed, yeah. I may not be undirected, but in general they're directed. So undirected is just bidirectional, basically. So yes, okay. But these links, yeah, even these links are directed actually. So I should not have drawn them as undirected. Even these links are directed. Okay, they're all directed. Okay. So what do we have? I mean, I've been telling you an abstract story, and I'm telling you that I don't have this, I don't have that. So what do we really have? So here's the data that we really have. That we crawled Twitter. In fact, we did crawl a bunch of, a pretty large segment of it. And then we have these user IDs. And then we have the tweets that they made, right? And then we have the timestamps associated with the tweets. That's it, really, right? And then we also have, let's say these, because we know the user IDs, we can crawl. If their network is public, we can crawl their neighborhood, and we can get the network of these users. That's all. So we have the user network. Let's say for a certain set of users, we have the tweets that they made on a particular time period, and we have the content of the tweets, and we have the timestamps of the tweets. This is really the only data that we have Right? And again, I mean, I'd love it if somebody takes this and say that, okay, the kind of problems I have can also be thought about in this particular framework. That I have a bunch of processes that I characterize. See, all of these. I mean, the content of a tweet is really, think of it as a noisy representation of the topic of the tweet. Right? It does not exactly tell you what the topic of the tweet is precisely, but it gives you some idea. Think of it as a noisy version of that. Right? The timestamp. It's a timestamp. There's not much to say about it, and the user-user network is the user-user network, right? We don't know the weights in the user-user network. Who's really influenced by whom? What do we want to say, right? We want to say that maybe things like this happened. Maybe this person sort of made this particular tweet, says that, okay, Syria strike puts US and US relationship with Russia at risk. That sort of influenced this other person to write this particular tweet. Right? Russia denies bombing US-backed Syria rebels. Maybe somebody sort of makes this tweet about Leonardo DiCaprio saying that we should not really be electing a candidate who doesn't believe in climate change. And maybe somebody puts out this other tweet that says that, watch National Geographic's stunning climate change documentary starring Leonardo DiCaprio, right? We don't know that this tweet was influenced by this tweet, or that this tweet was influenced by this tweet, or that this tweet was influenced by this tweet, right? But this is what we want to find out. This is what we want to try to model, right? That if we pose a sort of believable sort of model of how these tweets are getting generated, how the users are influencing one another, how the topics are influencing one another, can I try to capture by sort of inferencing the value, the parameters of the model, can I try to sort of say that, predict that, okay, it's likely that this particular tweet influenced this tweet? I mean, that also has two components. Was it that this person influenced this person, or was it that this topic influenced this topic? In this case, maybe these two topics are more or less the same, right? So we'll also try to understand that. Right? So then there's the basic problem, right? That we want to take this entire large collection of tweets that encompasses the users and the contents and everything, and we want to separate out these conversations, right? We want to separate out these conversations, what are typically known as cascades. That says that, okay, user one said something, and that is what, according to my model, I think with high probability, that is what sort of pushed user 2 to put out this. That is also what pushed user 3 to put out this. And so this is what this is what I denote by this relationship that I'm calling a parent. So think of it as a tree that is growing. A cascade is really a conversation tree that is growing. Right? I'm saying that the parent of this particular tweet is tweet 1, the parent of this particular tweet 3 is tweet 1. Maybe here the conversation is going like this. That this person is saying something about Trump signing a bill, this person is saying something else about that bill, this person is sort of now saying that, really, these are the critical missions, these are the most vulnerable missions under this administration, right? This is basically what we aim to do. Okay? What is the motivation? Okay, there's a bunch of motivations, right? First of all, as you can probably guess, that because this work was sort of inspired by some questions that TCS research had, and in fact also IBM had. Srikanta was at IBM when we started this. That they really wanted to understand this question about influence propagation in little bit more details. Right? Because until now, influence has really been which users should I seed with influence, should I seed with in order to talk about one particular topic, so that users can propagate, what those users say can propagate to the network. This is a little more refined. We're not just saying which users, we're saying that, okay, if this user talks about this particular topic, topics also influence one another. So which topics should we sort of seed the user conversations with, so that it sort of goes along one direction. That's one way to look at it, right? Another way to look at it is that if you talk about different other kinds of processes in which specifically, now, I should not say we are now looking at it. We want to look at some biological examples in which the user-user network is maybe the protein-protein interaction network, and these are essentially some things that are some beeps that are happening in each of these proteins, some action that is happening, and we want to say that okay, this reaction influences this reaction influences these two reactions, and this is how the cascade grows. This is how a reaction sort of spreads through this interaction network. Right? This is broadly the story that we want to build. Any questions here? Yeah. What decides the parent? So this is what the model will infer. Right. So see, the model. What we'll say is that what we'll try to say is that as I said, that if I have a particular tweet, right, it's possible, and we'll really come to it in the model, it's possible that you sort of generated the tweet out of your own interest. That's one possibility. So nobody influenced you. It's possible that you are just saying, you're just almost repeating what if I am always influenced by you, maybe I'm almost always just repeating what you are saying. That might have, and then my tweet's parent will be, the corresponding tweet that you made. That's one possibility. It's also possible that, okay, that I don't mimic you, right, but I engage in conversations with you, right, and the topic that you talk about sort of also immediately influences this corresponding topic that I wrote about. In that case, it is also, your tweet is also a parent of mine, right, but in terms of the topics, right, but these are not observed. Right? As I said, that only observed as the tweet contents, which user tweeted, and what is the content. We want to say that we want to derive this out of the probabilistic model that we will create. Right? That these trees that we draw will be the output of the model. Any other question? Okay. We know the social network. Okay, let me say for now that we know the social network, we know the skeleton of the network. We don't know these weights. So that is just a follow network. The tweeted follow network. Who follows whom? Right? That's all you know. But you don't know from them that I really read the tweets of this particular person very carefully. That you don't know. Okay. Okay. So here is our result in one, our sort of model in one slide. What we say is that really this is going to be modeled by what is known as a Hawkes process. What is a Hawkes process? I'll give a very simple explanation. And this is really going to be modeled by two things. There are two things that are coupled. It's kind of, so you can think of a conversation as essentially a sort of a Hawkes process in time, as well as a Markov chain over topics. Why is it a Markov chain over topics? Markov chain over topics means that if you look at the things in as we are talking, right? If you look at this set of lectures, you can kind of think of it as a Markov chain as the topics change from one to another over the span of one lecture and along consecutive lectures, right? This is what I'm referring to as a Markov chain over topics, right? This is how we model it basically. Right? And we do, and we show some way of inferencing it. Of course, I won't go into very much details of the inferencing. I'll just tell you a very, very high-level idea of how to sort of infer these models. So this you can, this kind of work, there's a whole lot of work like this. There's only one of these works, right? And this kind of results, you can think of it as the boosted plus of whatever kind of generative models we are talking about. Okay? Yeah. So for instance, here's a snapshot of our results. Right? See, one easy thing to do, there is this retweet functionality in Twitter. One easy thing to do, and that, what does it do? It basically puts a copy of the tweet with the saying that this is a retweet of the tweet, and if you crawl Twitter, you will get a sort of a ID that this is really a retweet of that. We're not talking about that. Right? Sorry. Of? Oh, Hawk's process, or I'll define it, because I didn't define it. So think of Hawk's process if you know Poisson process. Basically, a process that sort of goes in time. A Hawk's process is, I have this habit of stepping forward. A Hawk's process is really a self-exciting Poisson process, right? So Poisson process is somebody whose rate is constant over time. A Hawk's process is saying that, okay, if I produce more things, I get more excited and that changes my rate. That's it, really. That's really what Hawk's process is, right? It's a generalization of Poisson process. So yeah. So here are some here is, for instance, here are some actual examples from the data, right? For instance, we say that, so consider this tweet about Gelman and tweeting about Snowden and about whistleblowing, and so here is one tweet and here is another tweet. Our model, for instance, identifies this tweet to be the parent of this tweet, right? Although you cannot really do that from, so at a human level, you can maybe understand it and say that, understand the contents of this tweet and say that, oh, it's possible that somebody tweeted this and that influenced someone to tweet this. At the computer level, the only relation between these two is this word Gelman. There's no words in common, and it's very hard to say that the hashtags are not common. It's very hard to say from a simple language model that this is related to this, right? But this is what our model does output. Right? And here are some examples, some other examples. So for instance, we took these hashtags from a bunch of parents, what we labeled as parent tweets, and a bunch of hashtags that we labeled as child tweets. Turns out that these are all about, I don't know, these are all about fantasy football, and these are all about baseball, right? Red Sox is a baseball team? Yes, no? Nobody here will support me or sort of contradict me. Okay. So it turns out that conversations about one sport influence conversations about other sport. So all I'm showing in this slide is that I'm showing you some anecdotal examples to say that our model seems to be doing, other than the metrics that we are sort of outputting, that seem fine. It also outputs some sensible things we have seen. Okay, anyway, so yeah. Oh, the top right thing. So this is transition topics. Transition topics, what it means is that, what I just said here, for instance, so topic is really sort of an abstract cluster of a particular set of tweets, right? Somehow what we see is that from a topic that contains these hashtags, right? We get to topics that contain these hashtags. Right? If somebody talks about this hashtag, some other people talk about this hashtag. So it turns out that these are all either Netflix shows or some TV shows, and then maybe it's really sort of, you can make sense of it by saying that people are actually carrying out conversations about TV shows. So talking about, although this hashtag might not be present in the child tweet, they are talking about TV shows, and so the fact that this is a parent, this kind of things appear in parent, and this kind of things appear in child is not that surprising. That's what it says. Yeah. No, the same word does not show that the topic is similar. It gives you only some indication that there could be some similarity, right? This is, what I'm saying is that these are some example outputs of our model. Oh, okay. So, okay. That is a completely different question. So, a good point. So, we have not done all the basics. So, in any kind of language modeling, any document, there is a standard way of encoding it. Basically, it's called a bag of words model, right? You just take the tweet, you decompose the words, you represent it as a set of these words. That's it. And what I mean by words, you can take individual words. If you want to be fancy, you can take what are known as bigrams, which are consecutive words and so on. But that's it. That is the representation of a tweet in our probabilistic model. Yeah. It doesn't show the relation between this word and this word, but it does show that these two words appeared in the same tweet. Yes. That is not very, the fact that bag of words, although being a simple model captures a lot of the information in the document is an established fact. There's a lot of work, basically that's really the only model that, that natural language processing people sort of take on. We're just, so there's no innovation there. I mean, that's a pretty standard thing. Any other questions before I move on? So let me tell you what this generative model is. Again in very broad sketches, right? So this is a cartoon of a Hawk's process, I think. So think of a Poisson process. A Poisson process is like saying that I tend to speak at the rate of 5 words per minute. Right now, but if we are carrying out a conversation, right? I mean, if I said 5 words, maybe you also tend to speak at the rate of 6 words per minute, right? But if I said like 10 words in the last 50 words in the last 3 minutes, I churned out a bunch of information, right? And that then changed the rate at which you produce information, and maybe that again changed my rate at of producing information. Right? So basically, these are Poisson processes that are self-exciting. This is called self-exciting, and this is what a Hawk's process really is, right? That basically, so think of one particular person outputting a tweet that has some influence on the second person, right? But this influence also decays over time, right? That immediately tweet, the influence will be high, and 1 hour after the tweet has happened, the influence will be low. Well, that's like old tweet. So the influence decays over time. So the rate at which the second, so think of the base rate at which the second person is producing a tweet, that gets a spike when the first person is producing a tweet, but that spike decays over time. Right? But then maybe the second person, and then here's the third person. She produced a tweet here, and that produced another spike in the second person, and the second person goes on, right? And the second person produced a tweet here, right? And that increased the base rate of the first person as well as that of the third person, and then these pinks are the new base rates, and these again decay over time until they produce a tweet, and so on and so forth. So this is basically, without going into the maths, this is basically what a Hawk's process is. Right? That you that you have a certain base rate of doing a particular action, you get influenced by others, increase your base rate, and that influence by others, it depends on the events that have happened, until now, and the influence of those events decays over time, and at some point you also perform an event, and so that again influences some other people, and so on and so forth. Okay? Yeah. Person 1 did some action here that increased the rate of this person 2 as well as this person 3 maybe, and so yeah. Now we talk about person 2. So that is the Poisson process. So think of it as there is an underlying Poisson process. It's just that its rate is now a random variable. It depends on what has happened before. Okay, this is how we're modeling it. So we are not deciding it. It's just a stochastic process that we're using to model how, when each of these people are taking actions. Just that the rate of these stochastic processes are also random variables that depend on what has happened until now. Make sense? Or doesn't make sense? Yeah. Yeah. So that's why I'm saying it is not a Poisson process, because the rate is not constant. In a Poisson process, the rate would be constant. Because it depends, because now the rate depends, as you're pointing out, on what happened right now. If something happened right now, then my chance of doing something suddenly spiked. So that is why Hawk's process is the right way, is a better way to model it. That's what I'm saying. Yeah. So maybe it's sort of, I think, I've forgotten what this is. So think of 5 ABC. I think we are saying that 4. Okay, I see. There is some tweet. Okay, I see. So 4 influence the rate out here, influence the rate out here, and maybe this person tweeted here, did another tweet here, and this person did another tweet here. So one person. So I guess what it says is that A, B, and C. Right, are really all, the rates of all of this are really influenced by this one event here. That's why we have the same label here, 5. That's really all. And both of these are happening at the same user. That also can happen, right? That propaganda, that sort of, you're so excited by these tweet or this blog post that you churn out multiple blog posts. Yeah. That's a good point. That's a good point. So to some extent it does. In the sense, as you will see, is that, for instance, here 1 influences 2, so the rate of 2 goes up, right? And it's decaying over time. But now 3 also does something here, and that adds to the rate. And so the resulting rate will be the combination of what it was until this point and the boost that it gets. That's what will happen. Yeah, sure. Yes. We are assuming that. So it is not that hard. I mean, we are assuming that it's really this set of people who are talking amongst each other. You could assume that there is some inherent outside process who's influencing everybody. That wouldn't be too much addition to the model, I think. That would just be somebody here, person 0 here, God here, who's influencing everybody. It was sort of okay. Yeah. Yeah, I mean, one difference I'm seeing is that if we are saying that if the threshold crosses, we don't have a threshold that says that if it crosses, it will fire, but we are saying that the chance of it firing just goes up. But yes, I see similarities here. But so we don't know what this. I don't know actually how. How would we calculate such a threshold? But
threshold activated models
and this rate-based models, there might as well be because I'm reminded of this formal similarity that was between the 2 influence models in this Kleinberg-Tardosh, Kempe-Kleinberg-Tardosh paper. There they actually formally showed that this threshold-based influence propagation and this contagion-based influence propagation are formally similar in a particular sense. It might be that something like this is also true in this Hawkes process, but I haven't thought about that. Thank you. Okay, so this is what Hawkes process is, right? Now, formally, this is what is happening, right? This is really nothing but a jargonish way of writing up what was there in the previous slide. There is a base rate for a particular user. Think of this as the user V. This is the base rate, right? This varies over time. It depends on what the political climate is today and so on and so forth, right? Plus, there is an influence. This is what the influence is for the users who are neighbors of the user. For the events, this is what the influence on the base rate is. The augmentation of the base rate is due to the actions taken by the neighbors of this user. Right? This is what the augmentation is of the rate. Right? And how does this augmentation look like? Well, each of these, I take this HT, so forget this HT minus and so on. This is really, I'm summing over all the previous events that have happened until this point, right? And for each of these previous events, I am sort of saying that, okay, I take the difference in time between the previous event and my current time. That is what is this delta T is capturing. That how far ago was that event in time? Because if it was very far away, if it was much long away in time, it won't influence me so much. I also need to capture how much, if you was the generator, if you was the user associated with that event, who was my neighbor, how much influence does you have on me? I need to capture these 2 different things, right? That how the influence decays over time, and how the user influence is coming into the picture. This is how the process. This is how the rate will change formally. Okay. What is and the form of this f of delta t doesn't really matter at all. You can take it to be any decaying function in time. That's it. As long as it's decaying with delta t, it matters. It doesn't matter. Exponential something doesn't matter. E to the minus x something doesn't matter at all. It's irrelevant. So now what is happening? Let's not go into this. Okay. Let me show you this. So now it turns out that you can kind of think of such a, you can kind of think of this process. Although it is different from Poisson process, you can think of it formally as really sort of laying one Poisson process over another. right? It's really by saying that, okay, you're just increasing the rate, you just have a baseline Poisson process, and then you're increasing the rate. So it's like saying that you add in another events from another Poisson process, you increase the rate, so you add in events of another Poisson process. And this is a very nice algorithmic way of sort of creating it, which was sort of pioneered by Michael Jordan, the statistician. Essentially saying that any multivariate Hawkes process can essentially be created by sort of sampling from the Poisson process itself. So I don't want to go into this, but I mean, except that the only way to sort of, the one way to think about it is that think of this pi L as sort of as saying, so think of pi 0, so think of a conversation. So think of pi 0 as the first thing I said that initiated the conversation. Think of pi 1, right, as the replies that maybe Shita Bro and you guys did, the first level replies that you guys did, that sort of continue the conversation. Pi 2 are the replies to those replies. Pi L are the nth level replies, nth level actions that continue this conversation and so on, right? And we can basically, it's not very hard to show that you can sort of create them out of Poisson processes. For creating documents. This is more standard, but it may be unfamiliar to you. So don't worry about all these boxes and squares and so on and so forth. This is you open any machine learning book, you will you'll get such a picture. It's basically saying that what you say is that there are some, we think of these, as I said, that we think of each tweet as a bag of words, right? We think of each topic also as a bag of words, right? And each tweet, you can think about each tweet about a particular topic. It's really just a sample from that original topic, wala bag of words, right? So think of it as follows. If New York Times today wants to write an article about politics, I take that article, and that article you can think of it as a random sample from all the words that any political document should contain. Basically, this is a very simplified view, but it's a very accurate view, right? And this is a generative model. This is what we call a generative model for a particular, any particular document. There are other aspects to it that I'm not talking about, that how do these original topics look like? Okay, now we go Bayesian and say that, okay, these topics are also generated from some meta-level topics and so on, from some meta-level distribution, or the Dirichlet distribution, so on. So let's not go into it and so on, because unnecessary complicating it for this discussion. And basically, every topic is really a sort of a probability distribution of our words. Every document from that topic is really a sample from that probability distribution. Simple as that, right? This is what this picture is showing. So, okay, so again, so forget, just blur out all the complication. Here is what is happening in the generative model. We say that the generative model, right, we say that first of all, we run this multivariate Hawkes process and generate the timestamps for the events, right? That it's as if we sort of generate that, okay, you talk, then I talk, then you talk, then you talk, then she talks. We generate these timestamps, and then we fill in these timestamps with the contents of the tweets. Right, and to fill in these contents, we now sort of say that, okay, maybe the first tweet was about topic 1, then maybe it influenced these other tweets, and those maybe if the first topic is topic 1, these are the other topics that this topic 1 influences, and the corresponding tweets are samples from that topic, and so on and so forth. Then basically I'm first creating the timestamps, sampling the timestamps for the tweets, then I'm filling in the contents for the tweets. At a very high level, this is what is happening. This is this complicated stuff is what is known as the generative model of the tweet. Now what is the problem? The problem is that there are a lot of parameters in this particular model, right? Effectively, for instance, as I said, the parameters are, what is the value of any user-user influence? What is the value of any topic-topic influence? What are really the topics? Right? And all those parameters are things that we will infer, right? Based on this model, that if I assume that this is how the world was created, right? And then I look at the data, the tweet data that I have, and then I try to fit this model onto that data, and that gives you the values of these parameters. right? And the way to do this is effectively known as something known as, I mean, this is pretty standard in machine learning beyond it. This is known as Gibbs sampling, I mean, Monte Carlo methods, things like that, this sort. But I mean, just to, show you, I mean, again at a high level, why this is a difficult problem. Here's a basic idea, right? See, what we said is that there are two ways in which tweets get influenced by each other. One is that maybe users influence one another. One is that topics influence one another. And in some sense, if somebody had given me this set of influences, I could have inferred this set of influences. If somebody had given me this set of influences, I could have inferred them. But now we have, both of these are unknown. So we have coupled the two, right? We're saying the topics are not known. Then, I mean, I don't even know how they influence one another. How will I do all this? Turns out you can. You can. This is known as, and the result of this is going to be what I mean. This algorithm that we call this inferencing of cascades, and what we will do is that, and the result of this will be as follows. We will say that we'll write down a probability like this. The probability that that suppose a tweet happens at this particular user, we'll say that the probability that the parent of this tweet is this particular tweet, that this tweet is influenced by this tweet, is a product of three things. It's a product of how the topic of this tweet influences the topic of this tweet, times how this user influences this user, times how these two tweets differ in time. Basically that. And then we will write down the probability of these happening and then infer these values. These are the unknowns. Is T, K, K prime, and W, U, V, all of these are unknowns. And even the labels of this as K prime, this as K are all unknowns. This is what we will infer, right? Yeah. Sorry, yeah. Before. This box. No. This is not a neural network. There's nothing about neural networks here, Nothing about perceptrons here. So nothing about perceptrons here. This has a very specific name. This is called a box diagram or something. It sort of says that, okay, I mean, this box indicates indicates that, okay, this beta was an input parameter. Based on that, I created a sample. This box says that I created a sample out of this distribution. This has a particular name. I think it's called a box diagram. You open any book on Bayesian non-parametrics, you will see this picture. This has nothing to do with a neural network at all. This is completely not deep. Okay. So again, I mean, without going into the details of it, we have a generative process, and now we run the inference to sort of infer all these. Basically come up with the labels for every particular tweet in terms of the topics, to understand the topic inferences as well as to understand the user influences. And the basic, at the end of the day, this is really the algorithm, right? It's known as, it's a Gibbs sampling, right? But to us, sort of people more inclined towards theory, it's really a random walk that you're doing. It's basically that. It's a random walk that you're doing, and you are effectively sort of doing the random walk so that you can sample from the posterior distribution, if you want more technical jargon thrown at you. So you do Gibbs sampling, and that leads you to sort of get effective parameter as posterior distribution. There are other models that do it, right? But none of them actually have been modeling. I'm not showing you all the details, but none of them have been modeling topic interactions. And here is what we did. That we really did collect a bunch of hashtags, around 5,000 hashtags, and around 500K tweets corresponding to these hashtags made by around 1 million users. As well. So this is the real data, and then we also did a bunch of experiments on semi-synthetic data. What I mean by semi-synthetic is that we took some amount, the user network was real, but then we assumed that the data is generated by your model. Kind of like cheating, right? It's saying that, okay, if the data is generated by your model, are we reconstructing back nicely? This is like the first sanity test, right? Because it's possible that there's a lot of noise in Twitter, so who knows? So typically you do a bunch of what we know as semi-synthetic experiments, as well as a bunch of experiments on real data, and then you compare it with a bunch of baselines. You compare it with the standard, what is known as the topic modeling baselines, some existing topic models, as well as simpler versions of your model. This is what we call the Hawks plus diagonal, which effectively says that there are no topic-topic interactions, and then you compare, right? I mean, effectively, without sort of, I mean, what we say is that in the semi-synthetic data set, here you know the ground truth. That's the niceness about it. That you know that, yeah, that seems you generated the data, you know that which tweet came from which topic, right? And then you run your model to try to predict, I mean, to try to see if your predictions work out accurately, right? That what you predict, does it correspond to what you generated it with? Right? And it turns out that you do pretty well in accuracy and precision and recall in terms of all the three tasks that you have. In terms of both the network reconstruction task, network reconstruction means that how well are you predicting the user influence values? How well are you predicting the parent tweet of a particular tweet? This is what we call the cascade reconstruction accuracy. How well are you identifying the underlying topic corresponding to a tweet? This is what we know as the topic identification. And see, all of these things you can do only in semi-synthetic data, because you need ground truth for this. It's like saying, I mean, how do you evaluate a supervised algorithm? You cannot evaluate, I mean, until you have labels. And for the real world data set, you do what is known as a held out log likelihood. That basically, what is a log likelihood? It says that, okay, you have some training, you have some data, you build a model on certain part of it and keep certain and don't use certain part of it. And then try to see that does your model, I mean, does the data that you have held out have high likelihood with respect to the model that you have inferred? This is known as a held out log likelihood. And even there we perform pretty well, better than the baseline. So yeah. See, I mean, the method is not similar. So the Gibbs sampling is similar to MCMC simulation, right? The inference method is similar to MCMC simulation. Semi-synthetic method is just a way, is basically saying that I generate the data and I know the ground truth, and then I'm trying to say that am I sort of, I mean, if I run the model by hiding the ground truth and only giving the data, am I able to reconstruct the ground truth well? This is what we call is the semi-synthetic method. And we call it semi-synthetic because for certain parts of it, we use the real, for the user-user network, we actually use the real user-user network. That's why we call it semi-synthetic. So basically, here's a summary, right? That we have an interesting way that we think that we have a generative model for sort of modeling textual time series from user networks, in which these time series have topics, unobserved topics, and these topics have topical interactions. It has this, and it has this interesting part of the model that couples Markov chains with this multivariate Hawks process, and we have a pretty efficient, pretty efficient inference method for it, because the largest data that we were sort of working on was 500K, and now actually it's grown bigger. We do have significant better results compared to the existing state-of-the-art baselines, and we can derive interactions. We can derive interesting insights about topical interactions that the existing models cannot. If you want, I can point you to the actual paper that has some actual sort of some conversations pulled out that are nice anecdotally. I somehow forgot to paste this in here. So yes, so what I'd love two things. Any feedback on this? Plus, anything that you can see that you have remotely seen that's related to it in other settings than Twitter or Facebook? Because those settings you kind of know. And I think I'll be interested to see what other scientific processes, natural processes, can these kind of things be applied to? Because my intuition is that, processes happening on a network are again pretty ubiquitous, right? And we do need to develop tools to model it. That's it.